Okay, so what can a graph actually represent? So this is basically the question of why do we care about graphs? It comes up in a lot of places. So if you care about the structure of a computer network, then you care about graphs. So we want to know, is computer A connected? What computers is computer A connected to? In this setup, well, it's connected to B and D, but it's not directly connected to C. There is a path between A and C, but you would have to go through B or D and B. So this can represent a computer network. Similarly, it can represent familial descent or family ties. So if you want to look at my family tree, this can be represented by my parents, Con James. I have 3 kids, my 2 brothers. And then this guy is actually, this is 2 bipartite, this is 3 bipartite. So this is K23. This particular graph. You can also ask the question, what if I have people at a party, the people at the party are represented by vertices, and there's a line between them if and only if they know each other. So the textbook here has 7.1 is centered on the question, if we have 51 people at a party, how do we know that there's always at least one person who knows an even number of other people? That can including be just knowing nobody. So the then so and the proof for that basically comes down to the theorem that they have in 7.1, which says for any graph, the number of nodes, vertices, odd degree is even. And there's a pretty simple reason behind this. So if I have the sum of the degree of vi over all i's, so this is just the collection of, so all I in big V will just be the collection of vertices. So basically we're summing up the degree of all of these guys. So that's going to be 2 times the number of edges. So 2 times the cardinality of the edges. So if we had an odd number of vertices with odd degree, then we would have this sum of degree of vi is equal to the sum of odd degrees vi plus sum of even degree. So I should just do this over vi in odd degree. Sum so degree vi. So that's going to be equal to this right here, is a sum of even numbers, so it's even. So we can write that as 2k plus the sum of, there's an odd number of these guys right here, so we can write them as the cardinality of odd degree plus the sum of 2k's. So basically I'm just saying I can write each of these guys as looking at like 2ki plus 1. So I'm pulling those plus 1s to have here, and then I would have a bunch of 2ki's over here, which again, even. So this is equal to an even number plus an even number plus an odd, which is odd. Therefore, it's not equal to 2 times the cardinality of the edge set. So that tells us that we must have an odd number of vertices, of an odd number of vertices that have odd degree. Sorry, an even number of vertices with odd degree. For by contradiction, we must have an even number of vertices with odd degree.